I think you're too tall for this microphone.
Okay.
Just drop
Is that good?
Yeah, and then just drop that in your pocket.
Okay.
My microphone, there it is. Now we have Dan Painter with IV&V Lessons Learned from Anomaly.
Okay. All right, my name is Dan Painter, and I'll be talking about IV&V lessons learned from a memory scrub anomaly. We'll go through the agenda briefly. There's nothing too complicated about this. One thing I did want to note is that kind of the way that we work is that, okay. Basically, the first thing we want to go over is an anomaly description. I just wanted to call that out briefly. What that's kind of like is, in the case of an anomaly, this is kind of where we have the detective at the crime scene, where he's kind of found a body and they find a guy with, like 1 shoe or 5 shoes or some combination of things. It's just kind of the facts that we've found from the anomaly. And from that anomaly, we go through and identify things that are related to that, try to build evidence to maybe what happened. And in a perfect world, we have we know actually what happened with the anomaly. And but that doesn't always happen. In this case, we don't know 100% what happened, but we've gotten to a point where we've gathered significant evidence that we can make some observations and hopefully derive some lessons learned for IV&V from them. And we're still in process of looking at this and testing in our JSTAR lab downstairs. So hopefully, if we get to a certain point, it may be able to be verified exactly what happened someday. We will see. Okay. So the first thing is, who are we? I'm part of a group here. It's a derivative of an old effort, but it's added some new scope and a couple other interesting factors where what we look at are software issues and anomalies. So anomalies that have happened on NASA spacecraft, or really any spacecraft in general, anything we can get our hands on. But our scope is kind of increased from our previous effort to include software issues that have occurred that might be relevant and to NASA IV&V. And from these, we try to improve IV&V processes, methods, and procedures. Another aspect that we do is try to keep an eye out for new technologies, things that are emerging from NASA spacecraft, and be able to communicate those and certain risks or things that may come with that. And also, just any issues that come across in the course of development are fair game as well. So one of our goals is to not just improve NASA IV&V, but maybe provide lessons to the software development community as well. That's something that's newer. So our anomaly description. Basically, this anomaly occurred on a NASA spacecraft. One of the things that we do to get some of our anomaly information is we agree not to say what spacecraft it occurred on. So, but this happened on a NASA spacecraft, a science mission, and the evidence that we have, or what we found, is that the telemetry results of a memory scrubbing application indicated uncorrectable errors at several memory locations in system memory. So system memory right by the processor, that's not a great thing to have happen. As an added dimension of that, some of the addresses that had been identified for these uncorrectable issues had multiple uncorrectable errors detected at those locations. And the third thing is, this wasn't an isolated incident, which is kind of an interesting factor, which we can talk about in the observations. But essentially an identical anomaly happened a few years later, and that anomaly hit the same piece of system memory, and there were multiple uncorrectable errors, along with correctable as well. Don't count that out. So what we're going to do to dive into this a little bit is talk about, to understand what we're seeing, how we see multiple uncorrectable errors in the same locations. We kind of want to look at how memory scrubbing was performed on the spacecraft, how, if we did have an uncorrectable error, how that was handled, and then how that was delivered in telemetry down to the ground. Because I believe one of the things that I may have glossed over was that we don't really know the number of errors that occurred, and there's a reason for that. So how is memory scrubbing performed on this spacecraft? I wish I could have inserted an extra drawing here. You guys are going to have to use your imaginations. But basically, there is a radiation-hardened embedded component that lies between the flight software, or lies between the CPU and system memory. So if you have your CPU here, you have this rad-hardened component, and then you have system memory. And that component was responsible for performing error detection and correction on the spacecraft. It supported, so that was done in hardware. It supported single error correction and double error detection, which means that a single bit error could be corrected and a double bit error could be detected. An uncorrectable error could be anything that was double or higher. There's no guarantee that something with 3 or 4 bits would ever be detected, though, because it could flip bits in such a way that it would appear to be something else. So the way that this component worked is that whenever a flight software application or whatever would write a piece of data to system memory, it would add error correction code bits to that on every write operation. And that hardware component was also responsible for scrubbing system memory along with a couple of other different things. And it was able to be configured by flight software. So basically, whenever your memory scrub application starts up, it pushes a configuration to this component, says, hey, you scrub these pieces of memory at this rate, and just go do your thing. And so it does its thing, and everybody's happy. One other factor is that in order to scrub the system memory on this spacecraft, this hardware component took about 4.7 seconds, more or less, to scrub all of system memory. That's just one of the things that will come into play later. All right, so we talked about what does memory scrubbing. How are bit errors handled? What we have here is any time that a memory interrupt is issued by this hardware component, it invokes an interrupt service routine in flight software. So that's basically what that looks like is just a chunk of code in flight software that says, hey, whenever I get an interrupt from this component, you do some stuff. And and that particular interrupt handled all kinds of different things from bit errors to just general status messages. But we're going to focus on how it handles bit errors mostly. The first thing that happened, regardless of what kind of interrupt was invoked, was that it pulls, the interrupt service routine pulls in, it reads a status register on the CPU and pulls in, well actually it reads a status register, not a CPU on the component, and pulls in a record of any errors that occurred. One note is that based on the hardware limitations of the component in the spacecraft, only 4 errors could be handled at a time. It's just the register could only hold so much data. So this ISR pulls in the next 4 potential error things and deals with them. This is just a little note of how the errors were formulated. The first part of the error had the address. Well, the combination was the address of where the error was detected and the syndrome of the error, which has to do with error detection and correction. If you have a single bit, it'll tell you essentially where the single bit error occurred within that address range. With the double bit error, it's not as helpful, but it does still report it. So this interrupt service routine performs some actions based off of whatever values are read from this register. And so we're going to walk through the logic of the interrupt service routine. So We have our hardware component generating interrupts. What happens when we get a correctable bit error? The first thing that happens is that the interrupt service routine, if the memory address which has been presented for this error has not been logged before, it logs it into a correctable error log entry table. In this spacecraft, there's two tables, one for correctable errors and one for uncorrectable errors. So if this error address has not been put in the table before, it puts it in the table. If that error exists in the table, it increments a counter, which represents the total number of errors which have occurred there. This particular table only had 10 entries. So if you couldn't put any more addresses in the table, it would just not do that. That was one of the limitations, is that within a particular cycle, which we'll talk about in a second, you could only hold 10 entries in that table. Another kind of subtle key point is for the interrupt service routine for a single bit error, there's no need for the interrupt service routine to really do anything to correct the error, because the hardware component was, which is in between flight software and system memory, automatically corrects the error. So basically, this component, if it detects a correctable error, will correct the error on its own, but it sends an interrupt to flight software and says basically, hey, I detected a single bit error, here's where it happened, just so you know about it. So the ISR doesn't really have to do anything with a single bit error. Now, an uncorrectable bit error, which is double or higher, it uses the same logic. It tries to store it in the table, so it checks and sees if it's in the uncorrectable error log table, two different tables. If it's in there, it increments a counter. If it's not in there, it tries to put it in there. Yeah, it tries to put it in there, and if it can't, that's too bad. But there is an additional piece of functionality in this. There's a special condition, and that is that, oh, this didn't come out very well. There's like a little thing there. But basically, you have a special condition, is that in system RAM, you have an uncorrectable error. So you can't fix the data that's there. You can't get it back. But at the same time, within your memory scrubbing routine, you don't want to detect it again. Because if you're going through, it's going to detect a double bit error every single time, and that's not something you really want. So what this particular project wanted to do is it did something kind of simple and clever, is that it just read the bits at that location where the error was, and it wrote them back. And what that did is it kind of fixes the error, because as we said previously, the hardware component will add check bits automatically to the data that you write to the device. So what happens when you read and write is you're reading out bad data and you're writing it back, but it'll automatically update the check bits in system RAM so that when the memory scrubbing routine comes back, it's not going to flag an error. The data you still have there is, we're going to say it's intermediate, which means that most likely it's bad and you wouldn't want to use it for anything. But there are some specific cases, for example, if two check bits got corrupted, where you might actually get data that was somehow useful. So at this point, it just writes the system RAM to make it so that I'm not going to detect it every cycle, and then it flags that error. So the main thing is each time an error is detected, the interrupt service, IRS, no, they're not involved in this. The ISR refreshes the memory location so that it isn't flagged again in subsequent memory scrubs. And this is just a note. The logical branch that logs something in a table and the logical branch that fixes the memory location, in essence, they're independent. So if there were 10 entries in the table, it would still fix the data on disk. It just logs 10 entries. So it should, for every call, it should fix the uncorrectable errors so they won't get detected again. It's still bad data, but you shouldn't detect it more than once. All right. So how were these errors reported by the spacecraft. So there's a memory scrubbing routine that gets pulled every 5 seconds by the housekeeping subsystem, essentially. And what it does is that every 5 seconds, it reads the tables that were populated by the ISR and creates some counters based on the tables of how many single and double bit errors are seen there, and it sends both of them off to the housekeeping task, and then that gets reported along with the locations where the errors occurred. That gets sent back down to the ground. So this high-level flight software routine executes every 5 seconds. The last thing that it does is it clears the log tables. So any entry in those log tables that were there before, they're now gone. Our summary so far is we have a hardware component responsible for the error detection and correction. It transparently handles single bits and generates interrupts in the case of memory errors. It takes 4.7 seconds to scan system memory. The hardware component issues memory interrupts, which are serviced by interrupt service routine and flight software. The interrupt service routine logs the memory errors into a table and refreshes a memory location in the case of an uncorrectable bit error. And finally, there's a flight software memory scrub routine at a higher level, which reports on the ISR log tables every 5 seconds and clears them. All right. So now we kind of go into a bit of the analysis, some of the things we saw in the description, and maybe how they were related, and how we don't know some data, and how maybe some of the data got populated. So one of the things we said in the original description is the actual number of uncorrectable errors was not able to be determined. The reason for that is that the log entry table was limited to 10 locations. So any bit errors affecting additional memory locations within the 5-second flight software memory scrub cycle are not able to be reported. So we don't actually know, and the counters are based off of the table. So we don't actually know how many errors happened or all the locations at which they happened. We just know the first 10 within 5 seconds. And then if somehow some pass to the next cycle, we could get the rest of those. So that is unknown. So the second factor, and this is the more perplexing one, is that the examination of the telemetry indicated that there were several entries in the uncorrectable error log table with a count of 2. So what's going on? The interrupt service routine should fix the memory at the error location to prevent a second detection. And also, the second thing is that a 5-second flight software memory scrub table should clear the ISR table when it goes through. So that tells us either one of two things. Basically, for that to happen, exactly what it says here. The system memory scrub, which is the hardware component, would have to have scanned an address, detected an uncorrectable bit error, fixed the error, logged it, and looped back around to the same address and detected the error again, all before flight software cleared the table. And that's technically possible because the flight software cycle is 5 seconds and the component is 4.7 seconds. But it's pretty dicey, it's pretty close. So it's an interesting scenario and it's plausible. This says there's 2 scenarios in which this could occur. That's not true. There's more than 2 scenarios, but we're going to talk about 2. More specifically, we're going to focus on 1. But basically, the 2 potential things that could have happened realistically, there's other things too that we're going to address maybe. By the way, we're submitting a white paper for this, which will be done when those are due, which are in a couple weeks. So that should have the full analysis up to that point of this. But the first scenario is essentially that a double bit or uncorrectable error occurred. It was fixed by the ISR, and then a second event occurred and hit that same error location all within one 5-second flight software scrub cycle. The second thing which could have happened is that the part of the ISR which updates the check bits so it doesn't get detected again didn't work or wasn't effective for some reason, and the 4.7-second cycle got back around just before the 5-second cycle cleared. So if you imagine it, it detected an error, looped back around, and detected a second error right really close to that location. It detected that error again for some reason just before the tables were cleared. Because if the tables were cleared, you wouldn't get a counter. You would just get two different reports of a different address. All right, so evidence for just scenario one, the probability is very low. A double SEU that created double bit flips or uncorrectable errors in the same location, it's kind of a low probability. So we're gonna say if there's something with a greater probability, we're gonna look at that first. Not that the first thing couldn't have happened, it's plausible, but we're gonna see if there's something with scenario two. So we looked at the ISR functionality related to reflecting the memory or refreshing the memory. And one of the things it did is it makes an asynchronous function call to a flush operation, an assembly instruction. So what you have to think here, and this is a very interesting factor, is that the interrupt service routine is implemented in flight software. So flight software is running on your processor. In between this flight processor and the system memory is this component. So you're making this call to refresh memory in system memory from flight software. Well, what actually happens is because you're working with flight software is in this particular case, you have to deal with the processor's cache. And so if you do a read and write back to that same location in memory, there's no guarantee that the actual value in system memory was updated. So what flight software is doing is you hit a cache line and it puts a line in the cache for it, and eventually it's going to update system memory to reflect the value that's in the cache. Well, your problem is that your hardware component, which is looking at system memory, doesn't use the cache because it's between the CPU and system memory. So that is reading the actual values of system memory, which they identified as an issue because they called this flush operation. So what they're doing essentially is they say, okay, we're going to read and write this little piece of data back to update the check bits. But I also recognize that that may not be reflected in actual system memory. So I'm going to call flush to flush this particular cache line down to system memory. Well, that particular flush instruction was an asynchronous operation. A synchronous operation in that case would have basically said, we're not going to exit the interrupt service routine until this flush occurs. An asynchronous operation says we're going to spin this off with its own priority, and it gets serviced whenever it gets serviced on the processor. So basically what you had in this case is that the flush operation didn't necessarily occur before the end of the ISR. And so this particular function handled 4 errors at the same time. So it called this flush operation 4 times and then exited. And there was actually in the code for this, there was an operation which was just a static wait. So it was just a sleep timer that said for 255 bus clock cycles, just wait, and then move on to the next flush operation. So the assumption there was, and this is, I assume the assumption was that they thought that within 255 bus clock cycles that the flush operation would occur. And so what we have here is we have some evidence, and we can't guarantee that this happens because we haven't tested it. We're going to try to test it, among other theories, is that potentially that because of the multitude of single and double bit errors, and this was a huge hit, by the way, that some, between the combination of flight software and other things, getting time on the processor, that some of these flush operations weren't able to push the values from cache down to system memory, and the flight software or the hardware memory scrub was able to loop back around and redetect the error before it was cleared by the higher level flight software memory routine. And so that would explain potentially how you could get a count of more than one. So that's plausible. Ultimately, the root cause of this is unknown. One thought is that radiation did it. From other evidence, we think maybe it didn't. There were there was no indication of any sort of solar flare or radiation events from other NASA spacecraft during that time. Also, this spacecraft had an instrument that would detect some level of radiation. There was no incident. There was no indication that that happened either. The other thing is that the anomaly occurred twice and affected the same address range. It was about a 4 megabyte chunk of system memory both times. Because both incidents affected essentially the same piece of memory, the fact that it's just an SEU due to radiation is slightly less. Another possibility is that there's a hardware problem with the printed circuit board or some sort of threading issue in hardware. So what did the project do about this? These are just observations, is that the reaction was to take no action. And the reason for this in both cases, and in the part of the anomaly that we have with the description, it says essentially that they luckily dodged a bullet. And so in this particular piece of system memory was not something that was terribly vital, so they were able to just continue as normal. Observations from this. So there was an EDAC scheme in place to check for these errors, but in which did identify the addresses of single and double bit errors, but there wasn't, at least from what we saw, an effective fault management mechanism to respond to the detection of uncorrectable errors, other than ground invoking a command or something to respond to it. There was some evidence in some older requirements that potentially a worm reset may have originally been in place in case of a double or uncorrectable bit error in system memory, but we didn't see any evidence of that implemented in the final product, at least so far. And so it's just an observation that there was a capability to detect these issues, but there, other than ground intervention, there wasn't necessarily a thing that could be done about it on board. Another observation is that there was the limitation of 10 memory addresses with data detected, kind of left the operators in the dark as to the extent of the issue and the actual location of where it hit. This is maybe one that's not going to make it in the final paper, but essentially this means that if there if the interrupt service routine could have potentially handled more than 4 bit flips at the same time, depending on several other factors and maybe a change in the algorithm, there might have been some slightly higher assurance that that we would have been able to sync with system RAM. There's not really any guarantee. It's just that potentially that could have occurred under some circumstances. So there was a slight difference between the flight software memory scrubbing routine and the hardware memory scrubbing routine. Understanding that was important for us to be able to determine and trace back some of the causes and factors involved in this anomaly. The fact that one occurred at 4.7 seconds and the other occurred at 5 makes understanding what happened, it makes some of the theories more plausible and helps us to understand what could have gone on and at least direct our analysis on where we could look. And so we're kind of moving to the IV&V lessons learned part. And these are just big walls of text. I'm not going to read these. We're just going to try to get into the spirit of this. And one of the things is we want this to kind of be a discussion as well. And so hopefully you guys can ask some questions too. But one of the main things is that the memory scrubbing routines that are used in NASA spacecraft are pretty well known. Like the actual algorithms to do error detection and correction, whether you're talking about Hamming codes where you're talking about something more complicated, those are usually well known and established, and it's not uncommon for us as IV&V to not look at those parts. And that may be a fair assumption. But one of the things that we see is that some of the supporting functions when it comes to dealing with these EDAC error detection and correction software, such as updating check bits or reporting of errors. Those things should be in scope for IV&V analysis, if they're not. So that's just a thought from that way. The second thing from a recommendation perspective is that we think, and one of the things we were looking at, is that the detection of uncorrectable errors shouldn't necessarily be an end to itself. There's some evidence in this that understanding the flight software error detection and correction response, basically flight software fault management, may need to take an active role in certain cases, whether it's remapping past something that's stuck, if potentially you have an uncorrectable error that's stuck in hardware forever, or being able to do a warm reset to reload flight software if possible. The wait for ground intervention response may not be the best from an IV&V perspective. So we need to look for evidence that fault management is taking an active role in dealing with uncorrectable bit errors from an EDAC perspective. One of the other things derived from this comes from the limitation of the 10 error reports. Within the anomaly description that we have, it was kind of obvious that the operators would have liked to have more information if they could about the anomaly. And the limitation with respect to recording these issues was at their disadvantage. And so as part of an analysis of EDAC, it's important for IV&V to support the reporting of the EDAC results to the ground. And this is kind of an interesting case, actually, because we were able to go through some of the older requirements. We didn't have the latest version, I don't believe, of the requirements, but it's interesting how this limit of 10 was actually implemented, and that there was a requirement for the memory scrub routine that, and it kind of makes sense. Oh, well, it does make sense. The driver for it is that the justification was that in the case of a large upset of bit errors, we don't want to flood our downlink with error messages because we may need to respond back, and we just don't want to flood our downlink with this kind of thing. So we want to limit, per housekeeping cycle, we want to limit the amount of issues, error detection, things reported to 10. So, which is fair. That's a very fair assumption. Now, the interesting part in this case is that there's nothing that says that we can't record as many uncorrectable errors that occur as we can and just report them 10 at a time. You know, so that was translated not as we report 10 at a time and log all the ones that we have so ground gets a good idea of what happened, but instead we're just going to report 10. And so that was just an interesting thing, and that from an IV&V perspective, it's important for us to understand that ground typically has to deal with these things, and so the better information that they can get on critical errors, especially in this case, uncorrectable error in system memory is not a desirable thing. So any information you can get on that is going to be beneficial. And this is kind of a mashup of a couple different things. This has to do with caching, synchronous and asynchronous operations. From IV&V perspective, it's important to understand with memory scrubbing how those kind of things can be involved with respect to error detection and correction. One of the main things is this particular spacecraft had its EDAC support implemented in hardware. So that hardware in between the processor and system memory had direct access to system memory. There are some spacecraft coming up in IV&V that are planning to use software-based EDAC, which is fine. There's also different types of caching that occur. There's write-through caching. There's write-back caching. If you have write-back caching, what that means is that everything's cached, and you have to. There's no guarantee of when it gets pushed to system memory, but it kind of optimizes performance, so people use it. If you have write-through caching, it means that anything, an update to the cache gets pushed to system memory. So if you have software-based EDAC that uses write-through caching, that's probably going to be more beneficial. A lot of the operating systems and hardware that we have and look at IV&V support both of those types. But it's important with respect to EDAC to understand if you're going to start hitting a caching issue and understand what kind of caching is used on your spacecraft. And if something has direct memory access, like an ASIC or something like that, and it can read from system memory where you have a value cached that's an update of that, like how does that work? So when evaluating error detection and correction, it's important to understand what your system's doing with respect to that. This just basically means it's important for us to see that basically the timing difference between the hardware memory scrub and the software memory scrub allowed us to do additional analysis and understand easily what was going on here. IV&V, if possible, should be aware of the differences in time characteristics between functions, if they can. And we understand that, especially with respect to hardware, it's going to be difficult or beyond the state of our practice to be able to identify the same rates. But in this case, this didn't happen, but the ISR and the memory scrub flight software routine both had access to this table which stored errors, and they operated on different cycles. And so because you're talking about an interrupt, there is some other things involved, that there is a potential using timing cycles to prevent access to shared resources isn't enough, is essentially what this comes down to. And so if there are timing issues with different timing cycles and different things acting on a shared resource, it's important to identify that. And this is an addendum, essentially, to that previous statement. And yeah. And depending on the criticality of that, we should determine if there needs to be an alert to say that, hey, there was a problem here, and verify that the data wouldn't be lost. So this is who we are and our team. Does anybody have any questions about the anomaly or any other things about the recommendations? Sure.
We only have time for one question, so we'll go ahead and take yours, and then we'll move on.
All right.
What happened when the 4 that were recorded by hardware overflowed? So you had 4 events that were recorded by the hardware.
Yep.
And so what happened if 5 happened before the ISR got to the view? That's another.
Yep. Yeah, that's a good one. I guess then the next interrupt would hopefully pick that up. Yeah, exactly. So it's a good point. All right.
Okay. Thank you.
Thank you. Oh, you didn't need this.
I did need that.